Hello everyone, welcome to the algebraic graph theory seminar. Today, Joseph Iverson from Iowa State University will tell us about cover those complete graph, equiangular lines, and the absolute bound. Joseph, please.
Okay, thanks, and thanks for the invitation to speak here. I think I should warn everyone that it was daylight saving time yesterday, and I'm still a little bit punchy from the time change, but I'm going to do my best here. Okay, this is joint work with Dustin Mixon, who we just saw a moment ago. And this is an old picture of Dustin, but it's inappropriate because this is what he looked like when we were thinking about this particular work. And these are the folks who funded this research. The NSF, the NSF currently funds me, so they funded me putting together this talk. But I was also supported by a summer faculty fellowship from the Air Force Office of Scientific Research. And some of this work goes all the way back to when I was a postdoc at the University of Maryland, and that postdoc was funded by the Army Research Office. Okay, so just in case I drone on too much eventually, and you'll get tired of listening to me, let me just tell you right now what this talk is all about and what the main takeaways are from this talk. So way back in 1992, Chris Godsil and his student Hensel showed that if you have a certain kind of cover of the complete graph, then this will produce equiangular lines. So actually, in that paper, they were talking about something called equi-isoclinic subspaces, whatever that means. But for a particular kind of cover, those subspaces will have dimension 1, and then equi-isoclinic, whatever that means in general. And for lines, for dimension 1, that will just mean equiangular. Okay. So these particular kinds of covers of the complete graph, there's something called distance, regular, antipodal covers of the complete graph. And then there are even more adjectives that we'll throw on the beginning there. But for now, let's just say DRACKN, right? Distance, regular, antipodal cover of the complete graph. And the lines, the equiangular lines that come from DRACKNs, they cannot reach something called the absolute bound, except for in one particular case. That's the first main takeaway from this talk. So equiangular lines, this is a classical thing in algebraic combinatorics, and a big question is how many equiangular lines can you have in a given dimension, say D, and complex space this will be. And the absolute bound says you can't have more than D squared equiangular lines in D-dimensional complex case, and so you might wonder, can you reach that bound? And I'm going to tell you that no, not from this particular construction from DRACKNs. However, it could be there's something else we introduce called ρ, and maybe these ρ can reach the absolute bound. Okay, so that's the story. Let me say just a little bit more about my personal thought process putting this talk together, because this is quite old. So actually, these ρ, this is something that Dustin Mixon and I encountered. We were not trying to find them. We were thinking about something else. We were thinking about something called doubly transitive lines, so lines whose automorphism group as a permutation group is doubly transitive. And then these ρ just sort of showed up and insisted that we think about them. And a special case of that are these abelian DRACKNs. And while we were thinking about all this complicated stuff, we realized this fact, that's number 1. And we realized actually that this is a consequence of a result really not due to us, but really due to Shane Waldron. And so we put it in the paper. But the paper is not really about this stuff. The paper is really about this other complicated thing. And if a person just wants to understand this result, they go to the paper. It's very hard to read because it's all about this other stuff. But meanwhile, this story is actually quite straightforward and kind of never appeared in the literature. And I never really talked about it. I don't think Dustin did. And so the story just sort of hadn't really been told. And I always felt a little guilty about that. And so the purpose of this talk is to ease my conscience and get this relatively simple story out there in the world. Okay, so the outline of the talk is, first I'll give background on equiangular lines in the context that I think about them. And then I'll talk about these DRACKNs, these covers of the complete graph, and what they have to do with equiangular lines. And this is also just background. And then I'll talk about this absolute bound for equiangular lines. And this is where I'll really explain why DRACKNs can't reach this absolute bound. And then after that, I'll talk about this generalization we introduced called ρ. And I'll talk about there's sort of hope, I would say, that ρ could reach the absolute bound sometimes. Okay, So let's talk about equiangular lines. All right, this is a slide I use over and over again in my talks. I want to talk about the problem of packing lines. So here I'm given n lines. I can't change n, and by lines I just mean one-dimensional subspaces. In a space of a fixed dimension, it could be real or it could be complex. And my job is to arrange these lines so that I don't have sharp angles, okay? So the analogy that I often use is that these lines are like kids in the back seat of a car. So your car is either RD or CD, and this is how many kids you have. They're like kids in the back seat of the car because they do not like to be near each other. So if you have siblings and you think that this is you and this is your sibling, then you see the problem here, right? Blue is too close to red, and you as the driver, or me as the driver of the car, I'm going to hear a problem about this, right? The kids are going to be yelling in the back of the car. Okay, so I pull over the car and I say, Blue, you're too close to red, and I move the kids until they look like this, and that's good. Okay, I don't like this with a sharp angle. I like this where my lines are spread out. That's the geometry. Personally, I'm not very good at geometry. I'm much better at linear algebra. So I want to turn this into a linear algebra problem. So instead of thinking about lines, I'm actually going to think about vectors. I'll choose unit norm representatives for my lines, and I'll put them in as columns of a matrix. So that matrix throughout this talk, I'm going to call capital Phi. Okay. Now, in terms of angles, so maybe this is one of my unit norm representatives. This is another one. Well, then the cosine of the angle is the absolute value of the inner product. Okay. Now remember that I want wide angles, like the dream would be a 90-degree angle, right? And a 90-degree angle, that would be like an inner product of 0. So I'm happy when this inner product is small. I'm not happy when there's a sharp angle. Like the worst case scenario would be if these kids are sitting one on top of another. That happened to me when I was a kid. Sometimes I had to sit on one of my siblings' lap in the back seat. And that would be like having an inner product of 1 here, okay? So that's bad, right? And the loudest in the back, like the source of all the screaming, is the max. It's the loudest, the biggest absolute value of an inner product, okay? So that's the coherence. That's like the loudest scream in the back of the car. And because I want to avoid sharp angles, I want that loudest scream to be as quiet as possible. Okay, so that's my job here. That's called the coherence. Okay, so why? Well, this talk isn't really about the applications, and furthermore, I should tell you that I'm not really an expert in the applications, but I just want to give some sense of why folks care about this kind of thing. So here's one application. Okay, you can use this to uniquely solve an undetermined linear system. So here I have a fixed coefficient matrix. It is short and fat. So it has more columns than rows. You think it has more variables than I have equations. I am trying to solve for x, and I'm given y here. And I want to solve for x uniquely, okay? So the context in which this historically arose was like this. So this kid's about to go into an MRI machine. And it's going to take a bunch of measurements. And each of those measurements are going to be sort of like a row. And it's going to produce a picture of the kid's guts. And that true picture is this x, right? But the data that will be received is somehow this vector y. Okay. Now, when this kid is in the machine, he's not allowed to move. Actually, this happened to me when I was a kid. I had to have an MRI, and they told me I wasn't allowed to move. And I went in the machine and I moved a little bit, and then they stopped everything and came out and they said, no, we were serious, dude. So they're not allowed to move while they're taking the pictures. In particular, they have to slow respiration for the kid who's going in the machine, so that his guts aren't moving around too much, right? But that's dangerous. This is a sick kid going in there. They don't want to do that for very much time, but the number of measurements they're able to take, like the number of rows here, is proportional to the amount of time you're in the machine. So if you want to reduce the amount of time the kid's in there, then you have to reduce the number of rows here. Okay. That's fine. And at some point you get to a situation where it's as if you have a square matrix over here and they really want to push it further. And the radiologists were asking, can we push this further? And as a mathematician, you might be looking at this and going like, I'm sorry, no. At some point, if you have too few rows, you're going to have a kernel here and you cannot uniquely solve for X, okay? Except for the radiologists were saying like, we know you're wrong. We know you're wrong because we take the picture that we get and we immediately compress it to a JPEG. So we throw away a bunch of information. So apparently we didn't need all that stuff. Why couldn't we have been compressing while we were sensing? Okay. So this is possible. And let me say another reason, like morally, this should be possible. Like even forget this thing about compressing. Sure, you're going to have a kernel, and so there will be infinitely many solutions, like the ground truth, the true picture of the kid's guts, and then a bunch of other things. But you know which one is the picture of the kid's guts. It's the one that looks like a picture of a kid's guts. Like all the other ones just look like white noise or something like that. But there's just one that looks like a picture of a kid's guts. And if you do an appropriate change of basis, looking like a picture of a kid's guts, well, really it's sort of cartoon-like. So adjacent pixels will have the same value. Adjacent areas will look the same. And you can do a change of basis so that it makes it so that the true picture is represented by a sparse vector, which means it has a lot of zero entries. Okay, so it's possible to get a unique sparse solution. So sparse means that you arrange it, do a change of basis so this has a lot of zero entries, but you need something else. What you'll need is that the columns of your matrix here have to be somehow very different. And I'm not saying what that means. But not only does there exist a unique, you can actually find it with an algorithm using a linear program, using linear programming, which the point is that's fast. Okay, so if these columns span lines with wide angles, then that suffices for very different, whatever that means. And if you have better coherence, like you have wider angles, then that will make it so there are more non-zero entries allowed in this vector, which you could take as sort of a sense of complexity. So you're able to take pictures of more complex things. Okay. So I want to take pictures of more complex things, and so I want a better coherence. I want a wider spread of angles between my lines. Okay, so that's all I'm going to say about the application. And from now on, I'm just going to talk about pure math. So here are some examples of optimal line packings. Here, if you have 3 lines in 2 real dimensions, this is the optimal, which I think we look at and we all agree immediately that's the optimal. Like I have 3 lines, and you see that I have 120 degrees between any pair of lines. And it's like, yeah, you got 360 degrees of a circle here, and there are 3 of you, so split it between you equally, right? So, okay, sure, that's fine. But now you go into a higher dimension. So here's 6 lines in 3 dimensions. And now it's not so obvious what it should mean to divide the sphere equally among 6 kids, right? So this is, but okay, this one looks really nice. This is actually a regular icosahedron. The lines connect antipodes, antipodal vertices of a regular icosahedron. So okay, I kind of believe that. But once you go beyond 3 real dimensions, higher than that, then I can't draw pictures for you anymore. I only understand higher dimensions in terms of linear algebra, and pretty quickly I'm just looking at matrices like this. So here's the optimal arrangement of 9 lines, or an optimal arrangement of 9 lines in complex 3-dimensional space, and it just looks like this. I mean, it's these columns, they span lines. Those are the best. But this is kind of the flavor of it. Pretty quickly, you're just doing linear algebra, thinking about matrices. Okay. Now let's talk about how you know it's optimal. So maybe you get in the backseat of your car and you shuffle the kids around, so it looks pretty good, and you're like, all right, that's fine. But how do you know that that's really the best, right? Because I want the best. Like, how do I know that I couldn't take all the kids out of the backseat of the car, put them back in a totally different arrangement, and locally optimize again and get something better? So I need some kind of certificate. And the certificate in this talk is going to be based on this bounds called the Welch or the Rankine bound. It's related to something called the relative bound when you're counting equiangular lines. And it says that if you have n unit vectors, which I'll call like this, phi1 through phi n, and I'll be talking about the matrix phi that has these as the columns. I have n unit vectors in d-dimensional space, either real or complex. Then this loudest scream, this largest inner product, the smallest I can make it is this particular value. And at this point in the talk, you don't need to pay too much attention to the particular value. What I want us to notice right now is the conditions for equality. Equality holds in this bound if and only if this matrix phi is what's called an equiangular tight frame, or ETF. So I'm going to say ETF a lot of times in this talk. Equiangular means that those inner products, their absolute value was constant for all pairs I different from J. Tight frame is some spectral condition. It says that if I take that short fat matrix phi and multiply on the right by its adjoint, that'll get a constant multiple of the identity. Okay, so what I really want us to take away at this point in the talk is that if I see these two conditions, which are really algebraic kind of conditions, then that is a certificate that the Welch bound was attained, and therefore the line spanned by those vectors, that's an optimal line packing. Okay, so I want to be looking for these two conditions many times throughout the talk. Okay, so here's an example of using those conditions to certify optimality. So here's that 3×9 complex matrix I pointed out before. And to check, so I'm just going to check that it's an equiangular type frame. For equiangularity, I'll make the Graham matrix, the matrix of inner products. Okay, and I look off the diagonal and I observe everything has got the same modulus off the diagonal. That's equiangularity. Then I just check this tightness. I multiply phi on the right by its adjoint. This will give me a 3×3 matrix, and it's a multiple of the identity. That's tightness. So because I see both of these conditions, that's an ETF, and that's a proof that this is an optimal line packing for 9 lines in 3 complex dimensions. Okay, this next slide is pretty important. I'm really not going to think, like everything so far I've been talking about this short fat matrix, I'm actually going to be thinking about a different matrix. And in this slide, there's going to be sort of an intermediary thing, and then we'll see this third matrix, okay? So in the last slide, I was telling you we're going to think about this equiangular tight frame, which is this short fat matrix. I have this tightness condition. I have this equiangularity condition. But actually, you can just think in terms of the Graham matrix, the matrix of inner products, okay? So here it is for that particular example. So like the tightness condition, well, I could express this tightness condition by the spectral theorem because this is self-adjoint. I could say, well, this is the same thing as saying the spectrum of this matrix is just a single point, n over d, okay? But this G, you see, this is just multiplying, this is phi phi star, now this is phi star phi. This is the same matrices multiplied in the other order. And the spectrum, when you multiply matrices in the other order, even counting multiplicities, algebraic multiplicities, you have the same spectrum, except for possibly 0. So here I had n over d, actually d times. Here I'm going to have n over d, d times. I still need n minus d more eigenvalues, and those will have to all be 0. Okay, so I could just look for that condition. And then the equiangularity part, well, that's just looking, like in the last slide, off the diagonal. I want to have, okay, I need to have 1s on the diagonal, but off the diagonal, I need to have this constant value I call mu. Okay, that's not quite the thing I'm really going to be looking at, because the information in this Graham matrix, you see, I can ignore all of these root 5s. It's really about these phases off the diagonal. That's something we call the signature matrix. Okay, so it's like, well, you could subtract off this diagonal and then multiply by root 5, and then you have this thing called a signature matrix. And it's sort of like these are equiangular lines, so I know that all of these values off of the diagonal in the Graham matrix, they have the same modulus. The interesting stuff is the phase, and that phase is what's being recorded in this signature matrix. Okay, so in terms of the signature matrix, what do I need? Well, it better be self-adjoint, just like the Graham matrix was. And now this tightness condition, well, up here where I said I want the spectrum to be just these two values, I could think in terms of a minimal polynomial. I'm just saying the g squared has to square to a multiple of itself. Okay. Now I can substitute. I could write g in terms of s and then solve for s here. And this says something about s. It says that s satisfies this particular quadratic. So that's the tightness condition. And the equiangularity condition is really just that I have 0s on the diagonal now and something unimodular off the diagonal. Okay, so sort of this condition about being self-adjoint and this condition about being equiangular, that's easy to produce. The hard part is getting it to satisfy this quadratic. Okay, but this is really the object we're going to be looking for for the rest of the talk. And so I think this is a great time for me to pause with a warning that no one will understand the rest of the talk if they have lingering questions about this slide. So let me pause and give everyone a chance to ask clarifying questions about this slide. Okay, then let's go on. Now, one last thing I need to mention about equiangular lines is that they come in pairs. So every ETF, so I said equiangular lines, ETFs come in pairs. Every ETF has something called a Naimark complement, which we'll see sometimes in this talk, okay? So there's an ETF, let's say the primal I call this capital Phi, the Naimark complement I'll call this capital Psi. And here are some things about the pairs. So if this was a D by N matrix, like I have D rows, N columns, or N lines in D-dimensional space, the complement will be in N minus D dimensional space. Okay. In terms of short-fat matrices, the tightness condition, you could interpret that as saying that if you multiply that short-fat matrix Phi by a constant, then you will get it to have orthonormal rows. And so because I can get this to have orthonormal rows, well, then you think about completing that orthonormal sequence to an orthonormal basis. Well, I can fill in some more rows to make this whole thing a unitary matrix. Okay, and then those other rows, that's basically the short-fat representation of this Naimark complement. In terms of the Gram matrix, this G, the tightness condition was that it squares to a multiple of itself, or you could think this is a multiple of a projection, orthogonal projection, because it's self-adjoint. So if I scale it to make this an orthogonal projection, well, I could do the identity minus that orthogonal projection, which is like orthogonal projection onto the orthogonal complementary space, right? And then if you rescale that, then that will be the Gram matrix of this Naimark complement. Or in terms of signature matrices, which I said this is what we're really going to think in terms of this talk, if the primal has signature matrix S, these are the phases, remember, then the Naimark complement, its phases, if you think about this minus sign, it's just going to be the opposite. Okay, so I'm going to have these sort of pairs that come up many times in this talk. Okay, so that's it for now about equiangular lines. That was sort of the first character in our story. And now let's talk about the second character in our story, which are DRACKNs, distance, regular, antipodal covers of the complete graph. So there's a thing you can do when you have a real ETF to produce a special graph. And this special graph is going to be an instance of a DRACKN. Okay, so here's just an example to show you what it is. You take an ETF like this 3 by 6, and you produce the signature matrix, right? The phases of the Gram matrix, like we were just talking about. And now I'm going to do another thing to the signature matrix. So I think of this signature matrix, the off-diagonal entries, I'm going to think of those as being elements of a group with 2 elements. And I am going to think about the regular representation of that group with 2 elements. So just acting on itself by multiplication. So the minuses give me a flip, like that's under the regular representation what a minus does, right? And the plus, that's the identity that fixes things. So entry-wise, I'm going to replace each of these minuses with this 2 by 2 block that looks like a flip, right? And each of these pluses with a 2 by 2 block that's an identity, all right? And then the zeros on the diagonal, I make those 2 by 2 zero matrices. Now this is going to give me a symmetric matrix of zeros and ones. It's the adjacency matrix of some graph. And that's the graph that I'm talking about, okay? In this case, the case that I'm really showing you here, that graph will actually be the skeleton of the regular icosahedron. Okay. Okay, now there's something special about this graph. So really we'll be interested in sort of going the other way. And really, it's kind of about this adjacency matrix. All of the special things that we're going to care about can be encoded by what happens when you square this adjacency matrix. So this adjacency matrix, if I square it, I get this thing. So I get this constant on the diagonal. That's like regularity, right? And then off the diagonal, okay, in this case, really, I have a constant over here. This is some kind of distance regularity condition, but really what's going to be happening here is that I sort of fill up all of these other blocks with stuff, and I have one value on like where my adjacency matrix was, and then I'm allowed to have a different value everywhere else. So I'm going to show you again some more examples of this, okay? So don't freak out, yeah, but it's something special that happens when I square the adjacency matrix, okay? And we'll see some examples. Okay, so here's how I will, in this talk, be defining a regular abelian DRACKN. And this is going to look, I think, kind of complicated. So we'll just take a little bit of time to understand this slide. So it's determined by a couple of things. First of all, there's a finite abelian group in the background, very much like how I had plus or minus 1, a group of order 2 in the previous example. Its order I'm going to call R. And then I'll have a matrix. A matrix I call B. This matrix, I understand to have entries in the group ring, right? So I'm talking about the algebra with one basis vector for each element of the group. So here, like instead of the minus sign, I'm thinking about it as the basis vector that corresponds to minus in the group with 2 elements. And instead of the plus sign, I'm thinking about that as the basis vector that corresponds to plus in the group with 2 elements. Okay, so I get this matrix with entries in the group ring. And I demand some properties. First of all, I demand that down the diagonal, I have all zeros, like in a signature matrix. I demand that off the diagonal, I don't have crazy linear combinations of my group vectors. Actually, I just have one of the basis vectors from the group. So a pure group element, you might say, off the diagonal. And then because I eventually want this matrix to be self-adjoint, I insist that the ji, so it's sort of this B is self-adjoint, that its ji entry is the inverse of its ij entry off the diagonal. Okay, so that's some stuff. Now there's this squaring condition, and the squaring condition is going to be in terms of this adjacency matrix. So just like before, I get this adjacency matrix of a graph out of it. And the way I do it is I apply the regular representation entry-wise to B. So like this delta minus, I apply the regular representation and I get this flip like that. So I get these blocks, okay? I do that entry-wise, and that gives me this matrix I call A. Okay, that matrix A, I want to be the adjacency matrix of a graph. And I think actually to many of you here, you'd think the graph is really what I'm talking about. But I need something to happen that when I square this A, I get a particular multiple of A plus a multiple of the identity plus this Kronecker product. Like take the all ones matrix, subtract the identity. So this is like ones everywhere except the diagonal, and then Kronecker with J. Okay, and I have a multiple of that, a multiple of the identity, a multiple of A. There's some multiple I call C here. Okay, now this object, yes?
The Kronecker product, the 2 different J's are of different sizes.
Thank you. Yes, these J's are different sizes. Yeah, so this J is an N by N J, and this J is an R by R J. Yeah, thanks for pointing that out. Yeah. Okay, now I have these parameters, and I record them. So I'll talk about an NRC DRACKN. So N is the number of rows and columns I had here. R is the order of my abelian group, and then C records this parameter. And I'm not even saying that this is, nowhere on a slide did I even say even what this stands for. You could take this as a definition of some other object, but really the deal is that this graph is going to be distance regular. It's an antipodal cover of the complete graph in terms of what you actually get out here. But for us, this will be the definition. And the important thing really is this quadratic. So let me show an example beyond what I just did. So here, my group is going to be the group with 3 elements, Z3. And I'm going to have a cover of the complete graph on 9 vertices. My group R has 3 elements. And then this sort of distance regular parameter C will be 3. Right? So for me, I think of the DRACKN really as being this 9 by 9 matrix with group elements, it's got zeros on the diagonal, off the diagonal. I have these pure basis vectors from the group algebra. It's self-adjoint, so like this delta 1, if you look at the corresponding thing across the diagonal, I get delta 2, where 2 is the inverse of 1 in this group. And then the real important thing, the squaring condition. So I would take this matrix, and then entry-wise, I apply the regular representation. So like this delta 0, that's the identity in my group. So that fixes everything, right? This delta 1, that's going to shift by 1. So there's this sort of translation, this 3 by 3 translation. The 2 shifts by 2. So I get this inverse translation. So I apply that entry-wise and get this great big matrix. This is actually symmetric. So this is the adjacency matrix of some graph. And that graph really is the underlying graph of the DRACKN. But what I care about is that when I square this A, when I square it, it looks like this. So I get some multiple of the A itself. Those are the 1s over here. And then n minus 1 times the identity. Those are the 8s going the diagonal. And then there will be some other multiple, this C, j minus I. So you think that's like all 1s, but with 0s down the diagonal. And then chronocored with j. So this is a fancy way of saying ignore these blocks on the diagonal, right? Everything except for the blocks down the diagonal. And I'll have C of those, so that's 3. Okay, so this is what I'm talking about. This is the quadratic condition that defines a DRACKN. Okay, now, why am I talking about these things in this talk? Because you can use these things to make equiangular lines. So this is the result that really goes back to Godsil and Hensel, but it was sort of amplified in this paper by these folks in 2016. And it says that you can take a DRACKN as I've defined it and use it to make the signature matrix of an ETF. So the way you do it is like this. You're given that B matrix that determines a regular abelian DRACKN, and you take any character, so any group homomorphism from gamma into unimodular numbers. Don't do the trivial one, but any other one. And you apply entry-wise. So like here in this example down here, I'm taking the character that maps Z mod 3 into unimodular numbers. And because this is a cyclic group, I just have to tell you where the generator delta 1 goes, and I'll make delta 1 go to a third root of unity, cubic root of unity. Okay, so I'll apply that entry-wise, right? So like this delta 0, that goes to 1. And this delta 1, well, that goes to omega. Delta 2 goes to omega squared. Entry-wise, I apply. Okay, now I have an n by n matrix with complex entries. I call that alpha hat of B, where alpha was the character, B was this matrix. The theorem says that this alpha hat of B, that is the signature matrix of a D by n ETF. So if you square it, well, you'll find that it satisfies a quadratic condition. And then if you unroll the eigenvalues, you'll find some D here. Of course, there's also a Naimark complement if I do the opposite of that. So that'll be the signature matrix of an n minus D by n ETF. The D here, I'm not telling you how, but there's a formula. You can get it from the DRACKN parameters n, r, and c. It's a function of n, r, and c. Okay, so for instance, I take that B that we were just talking about. I apply alpha hat of B, and I have this signature matrix. Now, in this case, if you look at the Naimark complement, you apply minus signs. Then from this, you can recover an ETF. Actually, it's the 3 by 9 ETF, the complex ETF that I showed earlier. Okay, but somehow it's like this 3 by 9 ETF was really the shadow of the graph that determined this matrix. Okay, the cover of the complete graph. Okay, so here I just have a few examples of this process. So maybe I'll kind of go. This isn't super important, but I just want to mention there's some cool constructions of DRACKNs. So here, if you're given a prime power q and any number m that's greater than or equal to 1, then you make 2 m-dimensional space over fq. This is a vector space over a finite field. You equip it with a symplectic form, and then this is some beautiful classical geometry that will determine a DRACKN. So the DRACKN, in the terms I've given it, it's like, well, its vertices will be really this entire vector space. On the diagonal, of course, I have to have zeros, but off the diagonal, the sort of the UV entry will just be apply the symplectic form to U and V, and that gives you an element of FQ. So FQ under addition is my underlying abelian group. This is a regular abelian DRACKN with these particular parameters. So you can apply the machinery from the previous slide, and you can get ETFs. These are the particular sizes. If you do this with Q equals 3 and M equals 1, so you get these two sizes. So this is sort of the 9-mark complementary size. You'll get 6 by 9, and the 9-mark complementary size is the 3 by 9. And actually, this is the 3 by 9 from the previous slide. So this is a thing you can do. I think this is kind of well known. So these DRACKNs were just the graphs were discovered, I want to say independently, but I assume independently. I don't really know, by Toss and Soma. This example was mentioned in this paper, and then Dustin and I gave this particular description. Okay, now there's another cool example from like classical geometry that I'll just mention. So if you're given a prime power q, it could be even or odd, then n will be, it turns out, q cubed plus 1. I'll think about three-dimensional space over fq squared, and I give that a Hermitian form that I just indicate with these parentheses. And then something weird about geometry over finite fields is you can have isotropic lines. So lines that in terms of this Hermitian form, they can't see themselves. So they think, like if you take a vector, it could be that its sort of inner product against itself is 0, even though it's not the 0 vector. So if that happens, then that spans what's called an isotropic line. It turns out this is exactly how many isotropic lines there are in this case. And I choose representatives for those lines. And then I'm going to use those to make my DRACKN. Now, my group, the underlying abelian group, will be, you look in the multiplicative group of fq squared. So that's a group with order q squared minus 1. It's cyclic. It has a unique subgroup of order q plus 1. That's the group that I'm talking about. That's my gamma. So I'm going to make a matrix that will have entries in that gamma. So everything in here will have order q plus 1. Okay. On the diagonal, I have zeros. Off the diagonal, I do this kind of funny thing. So much like in the symplectic case, I just evaluate on the line reps. But then in order to land in here, you might think, or you might think like to account for the fact that these were line reps, I raise to the q minus 1 power. And then it turns out to make it a DRACKN, I need to put a minus sign there. But okay, I do this funny thing that's basically applied, it's applied the Hermitian form to the isotropic lines. And then I'm telling you that this will actually give you a regular abelian DRACKN. And the underlying lines have beautiful symmetry. The DRACKN parameters are what you see here. And then these are the ETF sizes. If you do this with q equals 2, you get these parameters that we saw before. Okay. Oh, this construction originally, and I didn't look up to see, but this basically is a construction of Chris Godsil from 1992. It was rediscovered independently by Matt Fickus and Dustin and some other folks in 2019. And then Dustin and I found it again in 2024 when we were thinking about doubly transitive lines. And this specific description appears there. I just took it from our paper. Okay, now, last thing I want to say about this is that the case r equals 2 is kind of different. So we aren't going to really think about r equals 2. It's very much the real case. So real ETFs are you could think as the same thing as DRACKNs with r equals 2 under this correspondence that I showed before. So this is an important thing. I don't want to indicate that it's solved or anything like that. These are equivalent to other objects. It's the same thing as what's called a regular 2 graph, or it's the same thing as what's called a strongly regular graph with k equals 2 mu. This is an important open line of research. It's just, it has a very different flavor. And so we're not really going to think about it that much in this talk. Okay, that was a lot of background. Now let's talk about the absolute bound. So I really want to talk about this problem. This problem was posed by Chris and some of his collaborators in a paper in 2016. It asks, does there exist a regular abelian DRACKN, NRC, where n is t squared minus 1 all squared, and r times c is this value? T has to be some integer, and I want it to be not 2. So why would I want this? Well, if it happens, then I get a d by d squared ETF. The d will be t squared minus 1. Okay, so in this paper, they say many things. They identify a ton of necessary conditions, and then they apply those necessary conditions, and they find many feasible parameters. So this table I just took from the paper. So they're not able, in that paper, their conditions are not able to rule out these parameters. Okay, and I'm a big fan of spoilers, so here it is. The answer is no. These do not exist, and that's what I want to tell you about in this section. Okay. So this is kind of what the whole first part of the talk is about, is why is the answer no? So before I tell you why the answer is no, let me tell you why you might even care. So this is related to what's often called Gerzon's bound, or sometimes it's called the absolute bound. And it says that if you have n equiangular lines in C to the d, and I should say here that d has got to be bigger than 1, then n can be no more than d squared. And furthermore, if equality holds, then the unit norm representatives, they have to form an ETF. So I'll just sketch here the proof, because it's a beautiful proof, and it's actually quite simple. The proof is this. You take unit norm representatives for those lines, call them phi1 through phi n, and then you make the orthogonal projections onto those lines, actually. So I just, pj is phi j star, right? Orthogonal projection onto the span of phi j. That's itself a joint matrix, of course. And then the point is that these p's, these are linearly independent matrices. And you can tell that if you just check out the Frobenius inner product between a pi and a pj, right? So because these are these outer products, then if you cycle a trace, pretty quickly you'll find the Frobenius inner product between the outer products is the entry-wise absolute value squared of, so the absolute value squared of these guys. These were equiangular, and so this is basically mu squared. You have that everywhere off the diagonal, and then some different value on the diagonal. But overall, the Graham matrix, like the matrix of inner products of these PIs, is this thing. This thing, you check out what mu is. Well, this thing will be invertible, is the point. So because their Graham matrix is invertible, then these things have to be linearly independent. And because they're linearly independent, I can't have more of them than the dimension of any space in which they live. Well, they're all Hermitian, so I can't have more of them than the dimension of Hermitian d by d matrices. And that's really where the bound comes from. This d squared is really, this is a real vector space, right? The real vector space of Hermitian d by d matrices, you can check, has dimension exactly d squared. Okay, so again, from before, this is about kind of hitting that bound. Now, it's not just, I think to Gerzon, this was, and I don't know if he even thought about the complex case. I wouldn't be surprised if he did. He actually was originally talking about the real case. This was some interesting, like, pure math problem. But since then, this has become very much an applied math problem. And the complex case is known as Zauner's conjecture. The conjecture actually is in the complex case. This happens for every d. There exists. You hit this bound, and there exists a d by d squared ETF. So I'll just sort of mention a little bit about the state of this problem and why people care. So if that happens, then those orthogonal projections, they will form a basis for Hermitian matrices. And this is essentially why this is important in quantum information theory. The state of the conjecture, there are numerical solutions for all d up to 53 plus some others, but all of them up to 53. And there are now exact solutions for all d up to, oh, this can't be right. I think these are wrong. I'm sorry, I think I have these switched. I'm not sure. These must be swapped. Of course, I would have more numerical than exact. Sorry, I think swapped. Yes, that's correct. For sure, these are swapped. Numerical up to 193, exact up to 53, plus some others, but only finitely many are known. There's some recent news that's kind of exciting, is that this Zauner's conjecture, which has been open for 20 years and a lot of people care about it, it is implied by the Stark conjectures from number theory plus some other conjectures. So like you might think this is like a strong version of the Stark conjectures or something. And by the way, this will be the subject of the talk in the Codex seminar tomorrow by Steve Lamia, if anyone's interested in that. It seems like it might be related to Hilbert's 12th problem. I have to tell you, I don't really understand that bullet point. I'm not a number theorist, but that's sort of the feeling. So maybe the takeaway from this slide is a lot of folks care about this Zauner's conjecture. We only know it in finitely many cases, and I think think this is really what this problem is about. So could we use DRACKNs to produce these sort of instances of Zauner's conjecture? Okay. So the answer I told you is no. And the reason it's no sort of has to do with a special thing happens. There's a special thing that happens when you have a d by d squared ETF. And it's really a consequence of the Welch bound. So remember this Welch bound. If you have n unit vectors in d dimensions, then the coherence can be no more than this particular value. And we're really going to care now on this slide about this particular value. Equality holds if and only if you have an ETF. So Shane Waldron observes that as a consequence of the Welch bound, if you have the signature matrix of a d by d squared ETF, this is very important, this slide, then you make the entrywise square, the Hadamard square. That will be the signature matrix of another ETF in this specific dimension, d plus 1 choose 2. Okay, so because this is such an important slide, I'm going to show you the proof. The proof is actually quite simple. It follows right from the Welch bound. So it's like this. You think about the outer products, and here when I say outer products, I'm talking about symmetric outer products, not Hermitian, but symmetric. So even though these are complex vectors, I'm multiplying by their transpose to make a complex symmetric, not self-adjoint, not Hermitian, symmetric matrix. Okay, so I make those things. Now I have d squared of those vectors here in symmetric d by d matrices. And think about their inner products. So here, when I make the Frobenius inner product, then this will be, I all of a sudden feel nervous about this, but no, this is right. This will be the square of the inner products I had before. And now if you read this direction of Welch, you see this was an ETF. And so I know what all of these inner products, their absolute value was. It was exactly 1 over the square root of d plus 1. And now I'm squaring that, so I get 1 over d plus 1. So I know the exact value here. Right, so this direction of the Welch bound tells me the exact value of these inner products, absolute value. Okay, well, they live in a space. So they represent, they span lines, you could think, equiangular lines in a space of this dimension. The dimension of d by d symmetric matrices is d plus 1 choose 2. And because the inner products are just the squares, the signature matrix of those equiangular lines, that's the Hadamard square. And now if I use this direction of the Welch bound, you plug this in for your dimension up here, and you observe that the Welch bound is exactly this value. And so these lines spanned by these outer products, they attain the Welch bound. Because they attain the Welch bound, then you have to have an ETF. So I'm really using this direction of the Welch bound now. So because the Welch bound is attained, then these outer products form an ETF in a space of this dimension, okay? This specific dimension. Okay, so that result is really why regular abelian DRACKNs cannot produce ETFs. So the theorem actually is if you have a regular abelian DRACKN that exists to produce a d by d squared ETF, then d could only be 1 or 3. And why? If you remember how we made these things, I was applying this character alpha entrywise to b. So alpha had to be, you apply this alpha entrywise to b. And the important thing is you get the same dimension for every choice of alpha. Okay. All right. So suppose you do this now, and you could be looking at an Imart complement, and you have a minus here. So let S be plus or minus alpha hat of B be the signature matrix of such an ETF. Well, then I look at its entrywise square. The entrywise square is applied by applying alpha squared, which is another character. Well, that's got to be the signature matrix of an ETF with these sizes. All right, so now apparently this is either D or N minus D. Oh, okay, actually it could be, I said alpha can't be 1. So if alpha squared was 1, well then when I apply that, I just get J minus I, and that's the signature matrix of lines in dimension 1. So you solve this equation, you find D is 1. If alpha squared is not 1, then you have this. This has to be either your D or N minus D. And you solve 2 equations, and you find D is either 1 or it's 3. And really, that's it. That's really the reason, is that you have the same dimension for any character. And there's this Waldron condition. I know that when I square the signature matrix, like using the square of that character, I know I have to have this dimension, which is like not D. That's really the point. Okay, so that's the very simple proof. I see I'm running a little low on time, but actually, I don't know. We started a little bit late. How much time do I have?
10 minutes?
I'm sorry, how much?
10 minutes?
10. Perfect. Thank you. Okay. So here is a table of feasible DRACKN parameters. So this is sort of leftover. Here n is at most 500. R is always an odd because I don't want to think here about r equals 2, odd prime number. And this is the resulting dimension. These are the DRACKN parameters. Here I put exists, but really I should have said known, and really I should have said known to me. So what this column means is if it's known to me that it exists, then I put a Y. If it's not known to me, then I say nothing. And like maybe it's known to somebody, but that somebody's not me. That's all I'm saying here. Okay, so here are some problems for folks to think about. This, a lot of, well, okay, my friend John Jasper is very interested in the existence of an 11 by 33 ETF. This is an unknown problem if there exists an 11 by 33 ETF. He's got me kind of interested in it too. But anyway, there are a lot of open problems here. Not always the ETF is, so for some of these, the ETF would be known. This is about if the DRACKN exists. But for many of them, the ETF is also unknown. Okay, so let me, in the time that remains, let me talk briefly about a generalization of DRACKNs we call RU. And I'll talk about, if I get there, an open problem, maybe some RU exists to reach the absolute bound. So what is a RU? Well, they're a generalization of DRACKNs, and there's a different perspective of DRACKNs that I'm going to use, and it goes back to this result of Godsil and Hensel. So instead of squaring A, you could square B, is kind of the takeaway from this slide. And there's a condition you want there when you square B. So I'm given, these are the first conditions that I insisted. So I've got this matrix with entries in the group ring. It's got zeros on the diagonal. I'm in the group off the diagonal. I'm self-adjoint. So all that remains is this squaring condition. So this B is a DRACKN if and only if when I square B, and here I'm squaring it in the group algebra. So this is as a matrix with entries in the group algebra. Then I get this kind of quadratic condition, which maybe it's easiest to look at this example. So I square this in the group algebra. So now I'm doing all my arithmetic in the group algebra. Then you get this particular thing. And what happens is you have 5 times the identity. Then you have 2 times alpha delta plus times B, 2 times delta minus times B. And you could write this n minus 1 times the identity plus some linear combination. You have some weight CG. You're taking that B matrix and multiplying it by scalars. And actually, this is saying you need very particular things to happen with these parameters. But for us, this is how we'll be thinking about it. Okay, and a RU is basically whenever you have that quadratic condition. So just like a DRACKN, it's determined by a finite abelian group whose order I'll call R. It's actually represented by this square matrix with entries in the group ring. I want zeros on the diagonal. Off the diagonal, I want it to be in the group. I want it to be self-adjoint. Now the quadratic condition is that when I square it, I get this multiple of the identity plus some constants times if you were to take that B, multiply it by delta G. And then the parameters I record with these CGs, right? So now the case of a DRACKN, that will be when these parameters, these are constant for G not equal to the identity. But there exists non-DRACKN RU. So here's an example. So here I'm going to have the fact that this is not also a 1 is a certificate that this is not a DRACKN. So here's a 4x4 matrix. You could think of this as a graph where that's the adjacency matrix. But as a RU, when I square it, and again, I'm doing the operations in the group ring. When I square this matrix, I get this thing. I've got 3 times the identity. And then I'll have actually 1 times delta 1b plus 1 times delta 3b. Notably, there's a 0 delta 2 here. But this is n minus 1 times the identity plus this kind of thing. Okay, so this is a RU. Now the graphs, I know this is the algebraic graph theory seminar, so let me just mention some properties of them. The underlying graph will always be a cover of the complete graph. To say that that's a connected graph is the same thing as saying you look at the group generated by the parameters that were not zero. You want that to be the whole group. If all of the parameters are non-zero, that's equivalent to saying the diameter. So then it'll be connected. The diameter is 3 is equivalent to this. And these conditions, either one of these equivalent conditions implies that it's actually a regular antipodal cover of the complete graph, like every vertex has the same number of friends. The spectrum of the graph spectrum, the spectrum of that matrix A is determined actually by the Fourier spectrum if you take the Fourier transform of these CGs. Okay. And you can take ρ and you can actually use them to make DRACKNs. So there's a quotienting move, much like you can do for DRACKNs if you're familiar. If you apply any group homomorphism from this gamma to any other abelian group, lambda, you apply that entry-wise, that will give you a ρ for lambda. The parameters you can compute just by sort of pulling back how big was the pre-image. And if you start with a connected ρ graph and you apply this quotienting move onto cyclic group of order p for any prime p that divides the order, you will get a DRACKN. So this is a way that you can get DRACKNs from ρ. It's not particularly important, but I think some of you might care. And then I care about them because they make lines. So if I'm given sort of these 3 setup conditions of a ρ, then the last quadratic condition is the same thing as always making ETFs in the sense of Godsil and Hensel. This is if and only if. So these are sort of the covers of the complete graph that produce ETFs. And the dimension you can recover with this Fourier transform. So here's an example. So here's the ρ I had before. I apply delta 1 goes to I get a signature matrix of a 2×4 ETF. And these things, we didn't make this up. We were sort of forced to think about them. We were thinking about doubly transitive lines. So all doubly transitive lines are ρ. That's why we had to think about ρ. But ρ also encompass DRACKN lines. They also, which in turn encompass all real ETFs. There are tons of complex ETFs that are not ρ. I'm going to skip this. But the problem I want to enunciate is about some feasible ρ parameters. So the problem, akin to the problem I told you before, the answer was no. Does there exist a ρ over Z4 with parameters like these particular values? So you can look this up in our paper if you want to look later. I want this t to be an integer bigger than 1. If that happens, then you get a d/² ETF. This will be the value of d in terms of t. The case t equals 1 is the slide that I skipped. It's something called Hoger's lines. But it actually works in that case. And all of the t greater than or equal to 1, as far as we can tell, are feasible. So we only have one integrality constraint for ρ parameters, and it is satisfied. The thing about Waldron's condition that I told you breaks DRACKNs, it does not break here. So if you check out the dimension of the ETF from the Hadamard square, that will satisfy the Waldron constraint. So that's fine. And then you might think like, well, does that ETF exist with this other dimension? That will actually be a real ETF, and that size will exist if there exists a Hadamard matrix, I should say Hadamard matrix of order this particular thing. This is a multiple of 4, so I assume it exists. Anyway, this is very feasible. So this is a problem I care about. I said problem, not conjecture, very intentionally. I don't know. I really don't know. I really, really don't know if the answer is yes or no, but just want to put it in people's heads. And finally, that's it. Oh yeah, this picture, I asked Microsoft Copilot to give me a funny picture of people with questions. And this is how weird Microsoft Copilot's sense of humor is. I also think it's funny. But anyway, these are the papers, especially this one that underlie this talk. So anyway, that's all I have for you. Thanks for sticking with me. And I'll be happy to entertain questions if there are any.
Thank you for the nice talk.
I have a question, which is what is going on with this guy's arm? It's a little too long. Oh, there's something in the chat. Oh, just thanks.
Hey, Joey.
Yeah.
Can you go back to the slide that you skipped so I can just stare at it?
Yeah. I'll let you stare. I won't interrupt your staring.
How much computation would it take to test your problem in the first open case?
You just called it my problem, but I'll remind you, Dustin, that it is also your problem. So the next open case would be pretty big. So in this case, t is equal to 1. So this is the solved case from this slide that was skipped. So when t is 1, the dimension is 4 times 2 is 8. So there I have 64 vectors. In the next case, t would be equal to 2. I would have 8 times 3 is 24, which is like kind of sounds good. But then I'd have 24 squared. Like I'd have a 24 squared by 24 squared matrix, which is sort of too big to really do much with.
And the Hadamard that has to exist, like how many, do we know how many Hadamards there are of that size in equivalent?
I do not know if that's known or not, but that feels kind of
on
big.
24, it's known. I mean, I don't know, and there won't be a whole lot of them.
Mm-hmm. So, but the kind of the issue there is that those plus or minuses, those are squares of something that I'm really looking for. And so it's like there are 2 possible square roots for each one, right? There's a, like the minus could have appeared as an I squared or as a minus I squared, and I don't know which one. And so there's a lot of ambiguity to try to track that down. I have spent some time trying to do that, but I think it's just too big even for this next case. Like I've tried to use like rank conditions to try to cut down the number of choices of square roots you're taking.
Joey, you have another question in the chat.
Oh, I do. Oh, thank you. I didn't see. Thank you very much for your talk. I wonder if there are more non-existence results for maximal real ETFs that can be constructed from abelian DRACKNs. Yeah, I think that is actually in the paper, in Chris's paper from 2016. So, and Chris, please correct me if I'm wrong, but my memory is that in that paper you showed that DRACKNs cannot be used to construct, this is the like real absolute bound, except for in cases that are already known. That's my memory. And please correct me if I'm wrong.
I'm sure your memory is at least as good as mine.
Well, I was looking at it the other day. So I think that
yeah,
that's
okay, so you got a second advantage.
Yeah, I have an advantage. Yeah, I think that the answer is that DRACKNs, abelian DRACKNs, cannot be used for that case. However, I'll point out that if there are other instances, and that's a big if there are other instances of real Gerzon equality, then all real ETFs do come from root. So they would necessarily be instances of root. Oh, sorry. No. I have to be wrong. I have to be wrong what I just said about what's in your paper, Chris. No,
I'm sure wrong about the paper, and there's not an error in the paper.
I think I'm not qualified to say this. Okay, please, I rescind my what I said was my memory of that paper. I think that's my memory is wrong. I don't trust that at all. Okay, also I guess there is a family of Roux graphs which are not distance regular. Namely, they are arc-transitive abelian regular antipodal covers of complete graphs, which arise within 3-dimensional unitary groups, but maybe it's known to you. They come together with unitary DRACKNs defined on page 14 of my slides. Well, let's go back and look at that. Sorry. These unitary, this is slide 14. There's a family of Roux graphs, not distance regular. They are arc-transitive abelian regular antipodal covers of complete graphs. They arise within here. Did I know this? I'm not sure if I knew this or not. So I could certainly make quotients of these. These will all be DRACKNs, but you're saying these are not DRACKNs. I don't know if I knew about that. That might be news to me. I'm not sure. My memory is very bad, but I'm interested in that. This is a beautiful situation.
Hey, Joey, while we're on the slide, I figure I'd set the record straight. You indicated that me and Matt rediscovered this independently of Godsil, and the truth is we were reading Godsil and trying to understand it. So we created a new way of capturing the same family. So it was not independent, but rather highly dependent.
Oh, okay. All right. Thanks for clarifying. And in that paper, I think you do not just make DRACKNs, like you make something that goes beyond that. Is that correct?
Yeah, we generalize in a direction of generalized quadrangles.
Right. Okay.
I can't resist a silly question. If I have a really big root, should I call that a kangaroo?
Yeah. You know, when we were making that, when we first encountered them, we didn't know what we were going to call them, but we really, really liked DRACKN and how that makes me think of a dragon. And so we wanted to call them DRACKNs. We didn't know what that was going to stand for. We figured we'd figure it out eventually, but then we realized that they weren't always, you know, regular. They weren't always abelian, antipodal. So we stopped. Okay, thanks everyone for coming and for your questions.
Thank you for the nice talk.